So today I thought we would continue our discussion of interparticle forces, so how all of the intermolecular forces combine to influence the interactions between particles and surfaces. So last time we did the simplest example, which is a molecule interacting with a sphere of similar molecules. Or I'm sorry, a molecule interacting with a surface, flat surface. And this is a surface of similar molecules. And what we found was that the net interaction energy. Now, whenever we talk about the interaction potential energy, we're really talking about the work required to bring that state into existence from infinite separation. From d equals infinity to d equals d. The potential energy of interaction, which could be negative or positive, is always relative to the separation at zero, or at infinite separation. The energy at infinite separation, which by convention we take to be zero. So something that goes from zero potential energy at infinite separation to separation at d in the case of particles, or r in the case of molecules. If it's lower in energy than at infinite separation, then it's negative. And if it's higher in energy, then it's positive. There's some conception that we have that something that has negative potential energy is favorable, which is perhaps a good mnemonic. Something that's positive is unfavorable, which is a good mnemonic. But remember that it's always relative. So the physical energy doesn't have a physical manifestation in these types of interactions. What has a physical manifestation is the force. So if the energy goes down as particles approach one another, that's a negative or attractive force. If the potential energy goes up, that is the negative derivative with respect to separation, then the force is repulsive or positive. Question.
Did you say
energy is a pessimist? Sure. Philosophically, it's interesting. At least I think it's interesting that what came first, the chicken or the egg? Did the particles know that their energy would go down if they got closer, or did they get closer because there was a negative force? So how do they know? There has to be some change in order for there to be a force, right? But if there's no change, how can there be a force? A molecule has to predict the future in a way. So WD we found to be minus pi c rho over 6d cubed. And the force is minus dw of d over dd, and that is minus pi c rho over 2 d to the fourth. And we got this by summing the interactions between this molecule and all the molecules in the surface. And we can come up with similar relations for other geometries. So what if instead of a molecule here, we had a sphere of molecules? So in this case, we have a surface and a sphere separated by distance d. Now remember, when we're talking about nanoparticles, we're always talking about the surface to surface distance, not the center to center distance, as we are talking about in the case of molecules. So we won't do the math here, don't worry about it, but for a sphere surface, interaction, we have WD equals minus pi squared C rho squared R over 6D. And because we get tired of writing the pi squareds and the C's and the rhos, we ball all that stuff up into a parameter called A, the Hamaker constant, and we have minus AR over 6D, where the Hamaker constant A not Hamaker, like John Wayne, Hamaker constant is pi squared C rho 1 rho 2. And the 1 and the 2 is if it's for different materials. If you have two different materials interacting, you have two different densities. So pi is pi, C is the Van der Waals coefficient, which is all of those Q squareds and alphas and all that stuff from 2 classes ago. Rho 1 is the number density, number of molecules or species within an object that is interacting with all of the molecules in another object. And this has units of stuff per cubic meter to make the math come out in SI units. We get the force in the same way by studying in the Jedi Temple. F of D, again, minus dWd over dd. And this is minus AR over 6D squared. Okay, one more, and then we'll talk about a relation between these. How about two flat surfaces? And in each case, just assume we're going through the hard work of doing all the integrations of all the molecules in one with all the molecules in the other surface. So what we're going to end up with here, this is surface. We're going to end up with a dependence that is energy per unit area. Because otherwise, what's the energy between two infinite surfaces? Well, depends how big the surface is. So you might as well just describe it in terms of unit area. And in order to derive it in that way, you need to define one of the surfaces as a unit surface. So one of something, like 1 square meter. In this case, we have WD equals minus A over 12 pi D squared. And the force, again, is minus D WD over dd, or minus A over 6 D cubed, and this is all per unit area. What is the force per unit area? Pressure. So this is sometimes called the Van der Waals pressure. Did I leave a pi out? Yeah.
Is this for charge surfaces or any sort of surface force?
This is any Van der Waals interaction. In general, this is a very powerful expression because from the Van der Waals energy and pressure between two flat surfaces, it's possible to get the Van der Waals energy and pressure between two curved surfaces. And what we're going to find, or what I'm going to tell you, is that if you have two curved surfaces with radii R1 and R2, the force between the curved surfaces equals 2 pi times R1, R2 over R1 plus R2 times the energy per unit area between flat surfaces of the same type. So if you can calculate the energy between flat surfaces here, but you have curved surfaces that are made of the same material as the flat surfaces, you just multiply it by 2 pi times the product of the radii over the sum of the radii, and then you get the force out. And this is called the Derjagen approximation. After a very famous Russian dude. Yes, sir.
So we're taking that the work function is identical for flat. This is correct? Or the geometric.
So the potential energy is the same between the individual molecules of which it's made, but the functional form between two different geometries is not the same. They have different D dependencies. So this is well, for energy we have d to the -1 here, and we have d to the -2 here.
So we end up integrating one function to get the results.
Yes. Yeah. You would integrate the intermolecular interactions from one to the other, from a molecule on one surface to a molecule on the other surface. But I would call it the potential energy function as opposed to the work function, because that means something else in this class. Okay. What are some typical values? Because this is a very theoretical discussion. I'm an experimentalist. I like numbers. So there's a medium. We have a C Van der Waals. So the medium is basically the material. Let's call it the material medium. Sounds like psychics. The Van der Waals constant has units of 10 to the minus 79 joule meters to the sixth, just to keep it intuitive, you know. The density has units of 10 to the 28 per meters cubed. These are good numbers to keep in mind. A molecule, a bite-sized molecule, there are about 10 to the 28 of them in a cubic meter. And then the A parameter, which is usually somewhere around 10 to the minus 19 joules. And this is the Hamaker constant. So how about a hydrocarbon? And this is CnH2n plus 2. C. Van der Waals, 50. Density 3.3 times 10 to the 28. And so pi squared C rho squared gives you a parameter A of 0.5 times 10 to the minus 19 joules. How about carbon tetrachloride? It's going to have a smaller or more or less Van der Waals forces. And this is, by the way, per CH2 unit. Otherwise, we're not comparing apples to apples. We're comparing this big, long polymer thing to some small molecules. We're just taking each unit of this CnH2n plus 2. So the Van der Waals forces between CCl4 versus CH2, which one wins? Which one has a greater Van der Waals force? I was thinking back from high school chemistry. The hydrocarbon would be right if we were considering the entire length of the hydrocarbon. But which one has more protons and electrons and a larger electron cloud to deflect in an electric field? That would be CCl4. And it's a lot larger, actually, 1,500. But the number density, because this is bigger, is smaller. If what I said made any sense whatsoever. The number density, because CCl4 is bigger than CH2, is smaller, because you can't fit as many of them in a cubic meter. So when you do pi squared C rho squared, you end up with the same thing. The greater Van der Waals force, but fewer of them in the solid chunk of stuff, say nanoparticles or surfaces. So the only parameter that ends up mattering, A, is the same. This is incidentally why, we know that Van der Waals forces are wildly different between molecules, right? I mean, if you took the chemistry SAT2 or some chemistry exam in high school, and which one has the greatest Van der Waals force or whatever, and it's like argon versus helium. Of course, it's argon, and it's argon by a lot. But when you go up to an object, say, oh, it's such a strong Van der Waals force, I can't get my finger off of it. I mean, that's a good thing, right? So it's the Hamaker constant, which tends to equalize these intermolecular forces so that, otherwise we'd be able to feel macroscopic Van der Waals forces, which you actually can if you're feeling for them. But it's why we don't have orders of magnitude differences when we're interacting with day-to-day objects. It's because of this push and pull between the Van der Waals coefficient and the density. Okay, so water. Water has a Van der Waals coefficient of 140, so it's less than CCl4, but it's pretty high compared to a hydrocarbon because of the hydrogen bonding. Its density is 3.3, and its A parameter is 1.5. So still in the ballpark, you're going to be somewhere around 10 to the minus 19 joules. So the point is that that no matter what the material, Hamaker constant always around 10 to the minus 19 joules. This is all for air or vacuum. In a dielectric environment, you can look these numbers up in a table. So if you're in a medium, it changes. It makes it a bit more complicated, but the Hamaker constants generally go down by 1 or 2 orders of magnitude, but they all go down. So typically in a table, you'll see lists of Hamaker constants like a silica nanoparticle interacting through water with another silica nanoparticle, or silica nanoparticle interacting through mineral oil with another silica, or gold through benzene with silver, or something like that. So you'll have a 3-part Hamaker constant: 1 material, 2 material, material 2, and then something in between. All right, so if all of these forces have a negative sign, they're all attractive. So why do things like nanoparticle formulations like sunscreen or paint or milk can be thought of as a nanoparticle formulation because it's proteins and milk fat globules? Why doesn't that stuff just always coagulate? Why doesn't it, or as we say in the business, flocculate? Why, my favorite word in science, why don't those particles just suck together by Van der Waals force if it's always attractive? Why are there any stable suspensions at all? Yeah. So emulsifiers, that is a way of providing structure to a suspension. You can put something in there like gluten or a gel or like Metamucil and shake it up, and that's certainly a way. But you can get stable suspensions without emulsification, and the reason this happens is because surfaces are charged, but the repulsive forces between surfaces that are charged, the fact that surfaces have the same charge is not really the reason why they repel. And this is quite an interesting point. So if everything attracts by Van der Waals forces, why are there any stable nanoparticle suspensions? And the answer is in large parts, but not entirely, because there are some other types of repulsive force, but this is the dominant one in most systems, are electric double layer and we call these EDL forces. So let me give you an example of milk fat globules. Where you have the total energy is the sum of 3 parts. The Van der Waals force, the EDL force, and what is called a steric repulsive force. This one is attractive. The other two are repulsive and keep milk from coagulating. Doesn't work for skim milk because it doesn't have any fat in it. Proteins are kept stable by electric double layer forces alone. Steric forces. Okay. So this part of the equation together, total force plus or equals the Van der Waals force plus the EDL force, is called the DLVO forces, named after one person named DLVO. Just kidding. It's named after 4 people. First one we met already. Steric forces. I'm going to tell you about steric forces in 2 minutes, and then we're not going to talk about it again in the course. Imagine 2 milk fat globules that have these protein chains that are free to flop around in solution. These are fat globules, and they have protein chains that flop around. Does anyone know what a koosh ball is? It is a rubber ball that has like 1,000 little rubber strands coming out of it, and you can play like hacky sack with them. That's kind of like what this is a ball of something with a lot of floppy chains around it, a lot of floppy strands. Now here, the chains have high or low entropy. Entropy is the number of statistical microstates that these floppy chains could adopt. Well, they could be like this, or they could be like this, or like this, or however. So high entropy. So here we have D before, and then we have D after. What happened to the entropy of the polymer chains? It decreases. So low entropy. Which one is more favorable, high entropy or low entropy? High entropy. Forget everything we learned about Van der Waals force. That's not important here. It is important for the ultimate stability of the system. But in general, if you confine things, that's bad. If you confine things, there will be a statistical mechanism to push the things apart. So the statistics say high entropy here goes to a low entropy state here. You want to increase the entropy again to lower the overall energy, and that produces a repulsive force. So when we talk about free energy, you remember delta G equals delta H minus T delta S. So the total energy of a system comprising more than just 2 molecules where entropy is actually important in systems comprising more than just two molecules, you have to consider both the enthalpy, which is a manifestation of the Van der Waals force, and bonds. So enthalpy equals bonds. They form, you have a negative enthalpy. If they break, you have a positive enthalpy. But if you have a multi-component system like this, you have to also keep in mind what's happening to the entropy. The reason I bring this up is because, and the reason why the steric force is repulsive is actually the same reason why the electric double layer force is repulsive. And here's why. First of all, why are surfaces charged? And in our discussion of EDL forces, we're almost always considering the case where the interaction is happening in water, because water is the most common solvent. It's also where biology happens in water. So the electric double layer always is present in water. So you never have a purely Van der Waals interaction. There's always some repulsion due to the electric double layer. Now, why does an electric double layer form? Electric double layer is a surface that's charged. So there's one layer. But then since you don't have, you can't really form an electric monopole in a solution, you always have some counterions around it. Like if it's charged with OH groups on the outside, which is what happens if you blow air bubbles into water, you actually get a negative charge from OH groups that interact with the air bubble. And then you have H3O plus ions that are around it, and those are the counterions. And they're not bound that tightly. They're bound a little bit electrostatically, but they can float away a little bit because of entropy, which is the first clue as to why this analogy also leads to the explanation for the EDL forces. So electric double layer is always present in water. And why? Because you can have ionization of surface groups suppose you have some amine, some ammonia group, some NH2 group. That's basic. So it will suck on an H plus and it will become NH3 plus. So that's what I mean by ionization of surface groups. You can have adsorption of ions. To a previously uncharged surface. Adsorption of ions to previously uncharged surfaces. This is like the case of a hydrophobic bubble in water where OH groups will spontaneously associate to it. Yep. So I'll get to how it relates to the EDL now. But the other part of the question, entropy, the energy goes down when entropy goes up. The entropy wants to be, it's just a complete backwards the way you described it to me. Entropy needs to be as high as possible. Yes. So the free energy is lowest when the entropy is high. Lots of statistical microstates available to any system of particles is always a good thing. And I'm using good and bad in a subjective way, in a, how did you describe it? In a pessimistic way. So it's like, entropy is like children in a room. You just put them in there, and when the adults are present, they'll behave, sort of. Then when the adults leave, they just start screaming and running around and being children. The third thing that can happen is charge transfer. Or acid-base. Reactions. So literally, like in the case of a quantum dot, you can transfer a charge. There could be some other type of reaction at a surface that changed the ionization state of the surface. I'm covering a lot here, but there won't be any. I'm trying to make it so that there's almost no new material on Friday, so that we can just review and go over what you need to know for the exam. So I know I'm doing this fast today. Okay, so imagine two negatively charged surfaces. The ions that are embedded in the surface, or the ions that are not going to dissociate from the surface, are called the co-ions. And then we have a layer of positive counter ions in a diffuse layer. Why are they diffuse? Well, they're associated, the ions are diffuse because there's some entropy. Just because it's better to be a little bit diffuse than to be completely stuck up against the wall with only one microstate available, which is very bad. What is the counterion density profile? Therefore, looks something like this. Why do the counterions build up on the surface? By the way, these two surfaces could be two flat surfaces, or they could be a really zoomed in view of the junction between nanoparticles whose radii were big compared to the separation. Does that make sense? So what is the origin of the counterion distribution? Why do the counterions associate with the sides, with the edges? And I know that nobody's saying anything because it seems kind of obvious. These are negatively charged and these are positively charged, so naturally, turns out that's not the case. The reason that's not the case doesn't matter what charge we have here. If you put a negative charge in here, what's going to happen to it? One negative charge. I like that answer. Any slice would shoot up or down. If these walls are infinitely large, which we can approximate if we have big nanoparticles relative to the separation. If we have a single negative charge in here, it's just going to float around. It's not going to do anything. Why is that? Because there's no electric field in the gap. If you have two of the same charge on opposite sides, there's no electric field, so there's no preference on where the charge is going to go. So let's say, so here's our one charge case, and it can just kind of go wherever it wants. Suppose we have two charges now. What's going to happen to them? They'll repel. So the reason they separate is because they repel from each other, not because they're attracted to the sides. Same reason, incidentally, why if you have a charged metal sphere, the charge resides at the surface, because charges are mobile inside of metal, so they automatically self-separate to as far away from each other as they can possibly get. No matter how many charges you add, they just keep going to the surface, going to the surface. So then the origin of the repulsive force, we have this diffuse layer of counterions. So the origin of the repulsive force say these are two spheres approaching each other, and because of some entropy, you have this diffuse double layer, and this is at some d before. But then what if you bring them up close to each other? Good, making good time. And this is D after. But now, because you're forcing the counterions to be much closer to each other than they might like to be, with respect to the entropy of the negative counterions, what's happened? Entropy is greater left or greater right? Greater left. We've reduced the entropy, and the fact that these counterions want more statistical microstates available causes a repulsive force between the two particles, between the two large particles or surfaces. So I've said a lot today. Questions about this? No more new material today. I just want to end the first 10 minutes of next class, I'll talk about one new topic, then 40 minutes of review. Yeah.
Does that mean you need to add ions in pairs so that you can have one freely moving around?
That's a really good question, and that is exactly why you can decrease the repulsive force by adding counterions to the solution. Because if you have an abundance of counterions, say you just take the salt shaker and you just shake in a bunch of salt, and you have lots of positive charges, but you also have more counterions. You have more negative charges. And therefore, what happens in that case is that the counterions get closer to the surfaces because it's less entropically unfavorable to confine them if there are more to begin with, because there are more counterions around than there are coions on the surface. You have lots of microstates available, lots of entropy, so it's okay to confine them more. And if you confine them more in the D before case, if these are even closer, then there's less of a difference between the energy in this case and the energy in this case, and therefore the repulsive force is less. And that's actually why if you take some nanoparticle solution and literally take the salt shaker and dump salt in it, the particles will coagulate by or aggregate. Coagulate is really irreversible. Aggregate or flocculate is reversible generally. That's one strategy for precipitating particles out of a solution. So even impurities or toxins or something that you want to get rid of. Yeah.
So following from that question, does it mean that we would expect DLVO forces to be stronger than, say, ion forces?
Yes. Yeah. You expect DDL forces to be stronger, that is more repulsive in water that has no ions in it. So it's really the balance. I mean, this seems like something, it's a little confusing, like how it works. First, why do the counterions segregate themselves to the sides the way that they do? And then how does entropy cause these things to push these particles to push themselves apart? But it's this sort of bizarre effect that is keeping us alive. We're like 20-ish%, depending on how much water you drank. The cell is like 30% solid stuff. The Van der Waals forces are huge, but because there are so many electrolytes and charged proteins around, keeps everything separated, keeps your cells from just collapsing into a Van der Waals mess of crap. With that lovely thought, I will leave you for this morning. See you on Friday.